Alright, so the point of this lab was to change some code that we were given in order to find the mass of a black hole. But before we get into that, I'm going to go over some of the objectives and what I'm going to do in this presentation. So the first thing I'm going to do is show some of the Python code. I'm not going to show all of it because that'll take a really long time. Show some important important equations, and then I'm going to address the what if question and some other questions that are brought up, and also the what does this mean question later on in the presentation. Alright, to the code. So first here I'm going to exit out of this, go to the code I've changed, and I'm going to show the new changed code here and the old code that were given without any changes first, so you can see the difference here. So starting off here, I changed the star.m value to what we were given, which is the mass of the star. But also changed the vector position of the black hole given here, and then we changed delta t to the number of seconds in one day. I added a little bit for the delta y. It originally didn't have the idx plus 1 minus the y idx, so I just added that there so we can actually get a difference for the initial, the final minus initial. And then here I changed the v initial, which is the vector of this. We added that. And then as you can see here, this was originally the 0 vector, so for p initial, just the equation for momentum is just mass times velocity here, so we just have star.m times the initial. We did the same thing with p final, and then delta v we just we do final minus initial. We do the same thing for delta p as well. Okay, so dp dt is just the change in p over the change in time here, and with some other equations we're given that fnet is equal to dp dt. P hat, when you find a hat vector, you have the value over the magnitude of the entire thing. So that's a knowledge we have to know. Just we're not given what p hat really equals, so we need to determine that through some prior knowledge that we have. And then there's some other values here, but I'm not going to go into explain all of these, but we know that dp dt equals dp dt of the parallel plus the perpendicular, so we can move the perpendicular to one side and then the dp dt to the other side and do some subtraction so we can get the one we want here. So in this case dp dt perpendicular, and then fnet perpendicular is just equivalent to dp dt perpendicular using this idea here. So that's about it for the changes. We also changed the arrow scale here. I changed this so the arrows aren't as large. But that's about it here. And then we added g. This is a given. We know this. This is a constant. So we have this here, and then I added this equation here to find the mass of the black hole. And I'll show you how we determine this in a little bit. Alright, here are some important equations. Just momentum equals mass times velocity. Fnet, this is we need to know this for almost all of physics. So Fnet equals dp over dt, and then this is just dp dt equals perpendicular components. So one is the parallel component and one is the perpendicular component. Alright, and now on to one of the more important equations for determining the mass of the actual black hole. So what we do here, we have the force of gravity equation, just big G times the mass of one object and then the other object and then the distance between them, which is r, the radius. Okay, and in order to find the mass of the black hole, which we are calling as m1, we have to move everything to the other side, which we do here. So we multiply by r squared, divide by g, and divide by m2, and that's what we get for m1. And now go into the code just to show that here. Alright, so as you can see, this is fnet, this is r, this right here. So we're finding the distance between those, and r, and then we're squaring it here. And then we divide by g times the mass of the star. Alright, I'm going to run my code. Alright, as you can see, here we go. Alright, and that looks great. Here we're given the mass of the black hole, and when it's put in on the WebAssign, this is the correct mass right here. That is that is what we want. So now we need to answer the what does this mean question. So we need to explain why FNet and DBDT are different. So in this case, FNet is the force acting on the star orbiting around. So that's the force of gravity. And DBDT is the result, or the momentum, after the force is acted on the star. So since this isn't 100% perfect, some of the force is going to be put out in other forms. So it could be heat, or it could be transferred to another form, and pieces could fall off the star. It's just not perfect, so it's not going to be exactly the same. And this is going to be a little less than 100% of FNet. That is why there's a difference between these. DBDT will always be a little less than FNet. If anything, it really can't be greater unless there's some error involved or something's wrong with the equation. Now we need to answer the what if question. So if the mass was changed, would we be able to tell a difference? And we would be able to tell a difference because we're given everything else. The only unknown we're really solving for is mass. So we can account for the change in mass there. But in this case, there is no difference. But the way we would be able to tell if the mass was smaller or larger would be if the mass was smaller, the star would just shoot off. It wouldn't be held into the same orbit and go farther away from the black hole. And if the mass was larger, if the black hole's mass was larger, the star would be pulled in tighter, and then it would keep going around the black hole until it reached the center and got sucked in completely. Alright, that's it. Thank you very much, and I hope you enjoyed this presentation.